So our last speaker is Rachel Houtz, and she will tell us about dynamical axions and gravitational waves. So you have 30 minutes.
All right, thank you. Can everyone hear me okay? All right, hearing no complaints, I'll continue, but let me know if you have any problems. All right, so I'm very pleased to be here today to tell you a little bit about some work I've done related to the topic of this conference, which is about relating dynamical axions with their gravitational wave signature. And this is work I did in collaboration with Gina Kroon and Veronica Sands. Gravitational waves are a potential probe of confining sectors. In order for there to be a gravitational wave signal, you need a first order phase transition. And I'm going to go kind of quickly because a lot of people have already covered this so far in the conference. But we have a reason to expect that confining exotic sectors can yield first order phase transitions and leave behind a gravitational wave signature. And there's been a lot of study in the past. Oops, sorry. There's been a lot of study in the past about using gravitational wave signatures to probe spontaneous symmetry breaking phase transitions. But recently, more attention is being turned to whether gravitational waves can probe exotic confining color sectors. And so if you have a confining sector, you would expect that there's a first order phase transition for more than 3 flavors, which you can expect from very general arguments. And so that means that gravitational waves could be a probe. And this is a very difficult thing to study. And so it seems like the first order thing to do is to use a low energy effective theory to try and parameterize the behavior of the potential of this theory at the critical temperature. But that's where the low energy effective theory breaks down. Recently, there's been some nice improvement to try and use lattice results to get a better handle on how to calculate this signal of these theories near the critical temperature. And Sandino earlier gave a really nice overview of these recent improvements. But one thing that I'm interested in is when you have a confining phase transition, often even if you're doing the first order approximation, which is to just use the low energy effective theory, the parameters in the low energy effective theory are not always very well motivated or not always very realistic. And so what I'm going to talk about is using a little bit of extra model building. Can you motivate the parameters chosen in the low energy effective theory of this confining transition to maybe get a slightly more realistic handle on what the gravitational wave signature might be? And so that extra model building is dynamical axion models. So it's very well known that you can solve the strong CP problem by employing an extra global U1 symmetry. When that symmetry is spontaneously broken at low energies, you have a pseudo-Goldstone boson, the axion. There is another solution to the strong CP problem, whereas instead of employing a U1 Petrikwan symmetry by adding additional scalars to your theory, you can instead assume that your theory has a massless quark. And if that's true, then under chiral rotation, you can actually remove the CP violating parameter just by field redefinition. And so this is an alternative solution to the strong CP problem. But if this massless quark talks to QCD at some scale, QCD then confines, and the massless quark forms a bound state. And that bound state can be thought of as an axion, which I'll call a dynamical axion. So the axions I'm going to talk about are not fundamental pseudo-Goldstone bosons, but are instead bound states. But this isn't too qualitatively different than the typical axion, right? This U1 symmetry is now the symmetry the theory is enhanced by this symmetry because of the existence of the massless quark. Under confinement, that symmetry is spontaneously broken and leads to a composite pseudo-Goldstone boson. But this leads to motivation for exotic confining groups, right? So one way is if you have these additional massless quarks, you need to hide them in a confinement group. And the old solution with the dynamical axion was the up quark being massless, but this seems to be disfavored by the lattice results or ruled out, depending on who you ask. And so if you have an additional exotic confining group, then you can add additional massless quarks and you can hide them in bound states that are held together by the strong force or by the force of this exotic confining group. And then also a nice thing about this is that you can effectively alter the MA-FA relationship to get visible axions. So the typical invisible axion has a pretty strict relationship on its mass versus dynamical scale. But if this axion talks to exotic confining groups, you can add extra contributions to the potential that induce extra mass sources for the axion. So there are some general properties of dynamical axion models that make them interesting to study from the point of view of their gravitational wave signatures. So every dynamical axion model, I'm going to move past the massless up quark solution, and now I'm talking about adding exotic massless quarks. So all of these models that exist in the literature have some very generic features. So typically what you need in these models is you need QCD, because you're trying to solve the strong CP problem. And you need the massless quark to talk to QCD. So it needs to be charged under QCD if it has any hope of being able to solve the strong CP problem, so that its rotations of the chiral rotations of the quark field can shift the CP violating parameter. Now, if you want to hide this massless quark in a composite bound state from an exotic confining group, this massless quark also needs to be charged under some dark SUN tilde. And so generically, like, you can play a lot of different model building games, but generically you always need at least these ingredients for dynamical axion models. And so what this guarantees is that the exotic confining group, when this exotic confining group confines, which we expect to happen at some scale much larger than QCD, from the point of view of this confining group, this one massless quark is charged under QCD, and there's approximately 3 flavors of the massless quark, because the QCD colors is an approximate flavor symmetry from the point of view of this exotic confining group. And so you're guaranteed to have more than 3 flavors at the confinement of the exotic dark group. And as I said earlier, this, based on analytical arguments, is where you would expect to find a first order phase transition. So very generically, you can expect that dynamical axion models will yield first order phase transitions when this exotic color group confines. And then you can see, like, so this is based on the analytical argument, but as you know, there's some stronger arguments from lattice. And I can show this where we might expect to see a first order phase transition on this nice plot that I lifted from this paper here, where on the x-axis you have the number of dark colors, on the y-axis you have the number of flavors. And for a very high number of flavors, you have an IR-free theory. Somewhere in here, the number of flavors and the number of colors balance, and you get the conformal window. And then below that, as you lower the number of flavors, in this white region, based on the analytical arguments of Pisarski and Wilczek, you would expect a first order phase transition in this white region. And then in the blue region is the crossover transition. And then these individual points have been verified by lattice. And the dynamical axion models that I'm going to talk about live in this region of the number of flavors and number of colors parameter space. So we would expect a first order phase transition. And finally, there's one more generic expectation for these models, which is that when these dark quarks, when this dark color group confines, you would expect to see pions in addition to the pseudoscalar axion formed out of combinations of these dark quarks. And because, as I said before, QCD is an approximate flavor symmetry, but it's not exact. We would expect quadratically divergent mass terms for these pions based on the explicit symmetry breaking from the fact that this flavor symmetry is really QCD. And so interactions with QCD drive the masses of these exotic pions up. And so we have generic predictions of the value of the mass for these exotic pions, which will have an effect on how we parameterize the low energy effective theory. All right, so let's talk about 2 pretty simple dynamical axion models. The first one is where we just have one massless quark in the theory. So it's sort of the simplest dynamical axion model. It's still a 3 flavor theory though, because from the point of view of this exotic confining group, this one quark is charged in the fundamental of QCD. So the 3 colors become 3 flavors. So the simplest theory is a 3 flavor theory. And And in this theory, QCD and the dark group are related by some discrete symmetry. And so it's like a mirror dark sector. That discrete symmetry is broken at some scale. And it's tuned so that the dark copy of the standard model is much more massive. So the dark color group runs faster and confines at a higher scale. The second, slightly less simple theory is the 4-flavor theory. So here you add 2 different massless quarks. One that's charged under QCD, so that gives you 3 flavors, and then another that's a singlet under QCD, which gives you the 4th flavor. And in this model, the dark color group and QCD are not related at all. And so in principle, there are 2 CP violating parameters, which is why you need 2 massless quarks. And because there's no relation, it's very easy to just arrange that this extra dark confining group confines at some high scale. So what happens when these dark groups, when the dark group confines? In both cases, you'll get a chiral symmetry breaking pattern at confinement. And generically, you'll end up with bound states that are composed of massless quarks. And some of them will be about the binding energy of the bound state. So you expect them to live near the confinement scale. And then the other bound states will be pseudo-Nambu-Goldstone states, and their masses will depend on the explicit symmetry breaking pattern of the theory. So first, let's consider the 3-flavor case. So again, the 3-flavor case is the one massless quark, but that one massless quark is charged under QCD, which at this confinement scale, QCD is still like a perturbative theory. And so this 3-flavor theory undergoes spontaneous chiral symmetry breaking, and this results in 9 Goldstone bosons, one which will form an octet under QCD, and one which will be a singlet, which will be the dynamical axion. And then what are the masses that we would expect for these pseudo Goldstone bosons? Well, the first one, as I said before, will generically have its mass lifted by interactions with QCD, since it's an octet under QCD. And so we have a generic prediction for the mass of this, this octet pion, octet exotic pion. And the second one will have its mass lifted in much the same way the standard model eta prime mass is lifted by QCD. Instead, this dynamical visible axion will have its mass lifted by the anomalous interaction with the dark color group. And so its mass will actually, this symmetry breaking, this anomalous symmetry breaking is a very strong explicit symmetry breaking effect, and it will lift its mass all the way up to the confinement scale about. And so we have one visible dynamical axion from this model. In the second case, where we have 4 flavors, which is really, these 4 flavors are coming from 2 massless quarks, one charged under QCD, one that's not charged under QCD. When the dark group confines, we have a slightly more complicated symmetry breaking pattern. So we can talk about the resulting Goldstone bosons from spontaneous chiral symmetry breaking. And then we can rewrite them in terms of their representations under QCD. And now we'll have pions, some in the octet of QCD, some in the triplet representation of QCD. And 2 singlets, which will be our 2 dynamical axions. And again, the masses of these pions will be determined by their interactions with QCD. So again, we expect the same generic relationship for the masses of these pions, although the triplet and the octet will have different group theory factors sitting in front when you evaluate this diagram. But finally, we'll find much the same effect that we have, like this is very analogous to the standard model plus an invisible axion. So there will still be this anomalous interaction that breaks U1A from these pseudoscalars interacting with the dark confining group. But this interaction will talk to both of these dynamical axions, and it will only be able to lift the mass state of one. And so when you diagonalize the mass matrix, you'll get one axion that's sitting at the confinement scale and another that won't get much of its mass from this interaction, and will instead be very light, so light that it mixes with the standard model pions, and we get this typical, the typical MA-FA relationship. And so this axion is an invisible dynamical axion. And in fact, this model was first written down to be a UV completion, another UV completion of the invisible axion model. So the low energy physics of this model looks much the same as the typical axion physics if you lift this scale high enough so that the visible axion is removed from the theory. However, there's more that you can do with these visible axion models. So you can actually have this 4-flavor model, and you can play some games so that you lift the mass of the lightest axion and you actually get visible axion models. So the simplest case is that this is a UV completion for an invisible axion model. But if you play some games with the color groups at high energy, here's an example of some research I was involved in, although there's more research along this direction to try and lift these invisible axion models and move these QCD axions around in the MA-FA parameter space. In this set of models, you can actually dramatically change the mass of the lightest axion by playing games like this. And so you can take a model where you have one visible axion and one invisible axion, and based on small size instanton effects, living at some very high energy, you can manage to lift the mass of the invisible axion. And so you can get 2 visible axions from this model. And I'm not going to talk about this in too much detail, but for the purpose of the gravitational wave signature, the point is that you have a lot of freedom on the mass of this light guy, whereas this guy is pretty fixed to being 1 mass scale. And where now I'm kind of being a bit free with notation, these are now the mass eigenstates. One is mostly made up of the massless quark psi, and one is mostly made up of the massless quark chi. So in general, it's possible to have a combination of anomalous effects that can raise both of the axion masses while maintaining a solution to the strong CP problem. So now let's talk about the gravitational wave signal. So at confinement, we have a phase transition. We chose to model the phase transition with a linear sigma model. So that's our low energy effective theory for these dynamics. Spontaneous symmetry breaking, it occurs through the sigma field getting a BEV, and then we can rewrite the sigma field as being a combination of Goldstone bosons and heavy states. One of the heavy states will be this phi field, and phi will be our order parameter such that when the VEV is phi is 0, chiral symmetry is restored, and the VEV of phi being non-zero implies chiral symmetry being broken. So again, the sigma field and the X fields are the heavy fields corresponding to the unbroken generators under spontaneous symmetry breaking. And the eta prime fields and the pi fields, these eta primes are our dynamical axions. These will be pseudo Goldstone bosons, and their masses will be due to the explicit symmetry breaking effects that I discussed earlier. So what we do is this here, what I've written so far, this potential, is the linear sigma model without any explicit symmetry breaking effects. So if we were to write down this model, we would find that the pseudo Goldstone bosons are exactly massless, as we've written now. So this is not a very realistic model yet to model the phase transition for the 4 dynamical axion models, which we know have explicit symmetry breaking effects. And so what we can do is we can add extra terms to this model to encode all of these explicit symmetry breaking effects. And so we can add one term, and this term is not really one that we came up with. This is a very common term because UN axial symmetry is badly broken in QCD, and so it's it's very common. And in fact, almost always this term should be written down to encode the UNA symmetry breaking effects. We also wrote down a term to incorporate the symmetry breaking effects that lift the pion masses, because all of our pions will be charged under QCD at this exotic confinement scale. And then we included a new contribution to capture the mass contributions from the small size instantons, since the small size instantons will only be talking to one flavor of the massless quarks. And so we managed to add one extra contribution to encode this small size instanton effect that can lift the lightest mass eigenstate. And so we know like the form of these terms, but we don't necessarily know the value of coupling constants that are realistic. And in fact, you might think that from the point of view of the UV theory will see a confinement, and so it has no information about the low energy effective theory. And you can think that you can't really see through this fog of confinement. But by making arguments on symmetry, you actually can extract some information of the UV theory and encode it in the low energy effective theory, because you can force the low energy effective theory to properly give you the masses of the pseudo Goldstone bosons that you expect, right? So if you write the low energy effective theory of the linear sigma model like this, you get this mass spectrum, which just comes from spontaneous chiral symmetry breaking. But as you add each of these terms, you lift the masses of these Goldstone bosons to be pseudo Goldstone bosons. And so based on what you expect the masses to be, you can write down justified terms for these couplings. So for example, You want this mu sigma parameter to be large enough that the visible axion lives at about the confinement scale. You can add this prefactor C here to lift the mass of the pions to be exact what you'd expect, maybe an order of magnitude less than the confinement scale. And finally, you can add this last parameter, mu SSI, and you can give it a value that tunes the visible/invisible axion, since this is the one we have the most control of, based on like effects in the very deep UV of the theory. And so you can like smoothly turn on the mass of this invisible axion and turn it into a visible axion, or tune it back down to being a light invisible axion. And you can model all of these effects with the low energy effective theory. And so from this point of view, we've now provided motivated parameters for all of these in the low energy effective theory based on considerations of the UV theory. So then the next thing that we do is model the phase transition in the early universe. So once we have the potential, the low energy effective theory, we can calculate at the thermal corrections and write down the finite T temperature potential, find the bounce solution. And we can see here this nice first order phase transition behavior at the critical temperature. We see the true vacuum start to evolve. And once we have the potential, we can sort of turn the crank, and we have the bounce solution. We can calculate the frequency and the power spectrum for the stochastic gravitational wave background based on this first order phase transition. And so this gravitational wave background that we're calculating comes from, in the early universe, at some temperature, patches of the universe go into the lower energy vacuum, the true vacuum. These patches have bubble walls, which have some energy density. These bubble walls collide with each other. And at some point, these collisions become complicated enough that the spherical symmetry is broken and gravitational waves can propagate nicely. And this becomes very, very difficult to draw. So I lifted this nice plot that has this simulation of these bubble wall networks. And this very violent process in the early universe leaves behind gravitational waves today that we can measure in detectors. And so what is the resulting gravitational wave signal for these dynamical axion models? So the first takeaway is that when you restrict the low energy effective theory parameter space, based on these considerations, you get a much, much weaker gravitational wave signal than if you can allow the parameters to be whatever you want, which isn't too surprising. And so for the very simple dynamical axion model, the 3-flavor model, we find that the gravitational wave signature is so weak that even like the most optimistic gravitational wave detector, the Big Bang observer that may ever be built, even its sensitivity curve can't pick up this gravitational wave signature for the dynamical axion models of NF equals 3. But an interesting effect shows up for NF equals 4. So in the case where, remember, NF equals 4, we have a lot of control over the ability to tune the mass of the lightest axion. And so what I'm showing here is the frequency versus the power of the gravitational wave spectrum. And we can see that the blue lines have better prospects of being detected in these proposed future detectors than the red lines, which are the signals of these models. And the red lines correspond to invisible axion models. So remember before I said there's a parameter in this low energy effective theory that we're free to tune to make a very, very heavy dynamical axion or a very light invisible dynamical axion. And so as we tune this parameter, we will change the value of the mass of the lightest eigenstate of the 2 axion system. And an interesting thing that we find is that the gravitational wave signature seems to prefer visible dynamical axion models, whereas invisible models, where these extra mu SSI effects aren't present, yield weaker gravitational wave signatures that we wouldn't be able to uncover. So the summary of this is that we've provided a study that gives prospects for gravitational wave signals for dynamical axion models with a confining scale of 3 TeV. They have some interesting features. Particularly, all dynamical axion models will have a massless quark messenger between QCD and the stark confining group. You're guaranteed, because of the fact that this massless quark is a messenger, you're guaranteed 3 light flavors and a first order phase transition. And also because of this massless quark messenger field and the symmetries of these models, you have generic predictions for parameters in the theory below confinement. And the new result is that the gravitational wave signature is very sensitive to the anomalous effects that raise the axion mass in the linear sigma model. But something that this is all great for the low energy effective theory, but we're interested in modeling the phase transition at the critical temperature. That's very important for the gravitational wave signature, and that's exactly where our theory breaks down. And so one consideration you might say is that, okay, so your gravitational wave signal depends a lot on these axion masses. The axion masses are coming from instanton effects, right? Whether they're small size instanton effects in the DPV, or some of them will be instanton effects right at the confinement scale of the Stark group. And so when T is much, much greater than the critical temperature, sorry, this is a typo. This is not GQCD. I mean, it is if you're talking about QCD, but if you're talking about the dark group, this is the dark confining group. But the force is perturbative above the critical temperature. And so you can use the dilute instanton gas approximation to calculate the mass of these dynamical axions. And this is pretty well studied. This dilute instanton gas approximation, however, has this IR divergence. And so you're forced to, and so you can either, if you're talking about the mass of the one that comes from confinement, you're forced to use the IR cutoff of confinement. If you're talking about these deep UV instanton effects, you can use a perturbative cutoff. But we know at finite temperature, this dilute instanton gas approximation tends to be suppressed. And this was talked about early in Villadora's talk. He talked about how the magnetic susceptibility at high temperatures is very suppressed. And so we know that if you go very far above the critical temperature, perhaps these mass contributions, which are responsible for the gravitational wave signal are above the critical temperature, they are suppressed. Below the critical temperature, they seem to contribute. And the question is, do they still contribute at the critical temperature? And that's a very pressing question, because that had a huge effect on the gravitational wave signal that we calculated. And so the point of this is that in our study, we found that the mass of the axion, which is induced by symmetry breaking effects of instantons, has a large effect on the gravitational wave signal of a confining theory. But we don't know much about the behavior of this parameter near the critical temperature. So in conclusion, these extra color groups, I think they're very interesting because they allow invisible QCD axion to become a visible QCD axion. So they alter the MA-FA relationship. And so all of the ALP parameter space now becomes QCD, or some of the ALP parameter space now becomes QCD axion parameter space, and you can now move things around in the MA-FA plane. Gravitational wave signals can probe exotic confining sectors. And it might be interesting to look at more complicated models so that you can inform parameters in the low energy EFT, if you're going to use the low energy EFT to model phase transitions. Although I think the work in the direction of using a better understanding these confining phase transitions using input from the lattice community is also very good progress in this direction, since that seems like a better way to get a handle on this signal. But based on our analysis, we did find that gravitational wave signals favor models where extra color groups provide an additional source of axion mass. Thank you.
All right, thank you. So, time for questions.
Hi, just a question. Have you thought whether you can embed your theory in or your theories in a grand unified model?
So there's actually some work on this. I didn't actually provide the citation anywhere in my talk. So maybe on this, the most natural place to put it would be on this slide. There's a group, I think Spanowski and Gupta wrote a paper, actually a group out of Durham. They wrote a paper about using gut theories to basically play the same game where at some high, so here's the confining scale, and some very, very high scale, you can have some other non-abelian gauge group can run to be slightly stronger, and then it's spontaneously broken. So you can calculate the small size instanton effects freely here, and you have a lot of control over them because there's no confinement here. The next confinement scale is here. And so they wrote a paper like playing a similar game, but I think they embedded it in the gut theory. So there is some work on this, but yeah, I haven't worked on that directly, but I know it's out there. Yeah,
thanks.
Yeah.
Do you have a question?
Thanks for the talk, Rachel. I have just a comment, perhaps minor from your point of view, but this is something which is of great interest in the lattice community, and it is the order of the transition for NF equals 3 or larger. And so the scenario you've been referring to, of course, a very well established scenario, very well theoretically motivated, but it is currently under scrutiny. And so if you are interested in hearing more, there is discussions this afternoon on these topics, because there are indeed possibilities that the transition remains continuous all over till the conformal window. And it would be good to know what happens to the models you have been discussing in this case. But thank you very much for your talk, Rachel.
Yes, absolutely. I would be very interested in hearing that, because I think it would totally kill the gravitational wave signal. There's no first order phase transition in this region. So yeah, I mean, I think that's a question that's very interesting to people studying dark confinement and the gravitational wave signal that results.
Any other questions? So actually, I have a question. So it's a general question about the approach. So when you compute the phase transition is along the radial direction of the sigma model.
Yes.
And these degrees of freedom are not degrees of freedom of QCD. Okay? They are completely different from QCD.
Yes.
So why this approach based on the sigma model, linear sigma model, should be reliable to describe the phase transition of QCD?
So sorry, we're talking about the phase transition of an exotic confining group. So we're not modeling the phase transition of QCD.
No, you compute the phase transition with this potential. Okay, yeah. So
yes.
So this has the right chiral symmetry breaking, so the Goldstone bosons are the same as QCD, yes. But these are not the relevant degrees of freedom for the phase transition.
Yes.
And the radial directions, they are completely different from the spectrum of QCD. So
yeah, so
should I believe that this estimate is reliable, or is?
So I would argue that I agree that near the critical temperature, this theory breaks down. And so like maybe perhaps there are better effective, like low energy effective theories. Although I'm not aware of a theory that can actually probe the phase transition where things all become non-perturbative.
Well, the problem is that this is not an effective theory of QCD. Okay, is another theory which has the same symmetry breaking pattern. Mm-hmm. So it could be that in real QCD the result is completely different from what you get from the linear sigma model.
So you're saying you're advocating for something more like the PNJV, like the Nambu-Jonah-Lassinio model and things like this, right?
Well, unfortunately, I think also that is not an effective theory of QCD. So I don't know how to do it, but I mean, I want.
I agree. Like this is a very important point, right? So like if there are like, and also like I think there's been some work recently in the direction of like functional normalization group to do a better job at this. Like I think Gina has a paper out about this. And so yeah, like this is a very important thing. So I think like at best when we did this, like this work was very new, and like the idea of even using gravitational wave signals of confining groups was very new. Since there's been a lot of new work trying to like better understand this. I think that, yeah, there's a lot of room for improvement, and maybe I think you can at least take this seriously enough to say that we didn't just pick whatever, like some of the other like models just pick whatever they want for the parameters in the like Nambu-Jonah-Lassinio model, for example. And we motivated the parameters, but I agree that near the critical temperature, like this theory breaks down. And so it would be better to do a better job. So this is at best, like take it with a grain of salt. Right. We found that the gravitational wave signal gets much worse when you use realistic parameters. But perhaps like this whole using low energy effective theories to model the critical temperature is maybe not a good thing to do at all either. So it would be interesting to see more work in the direction of doing a better job at this. Yeah, I think there's definitely improvement to be made.
Yeah, thank you. Okay, so we are, I think, ready for lunch. Let's thank Rachel. And we reconvene at what time?